Well, hello everyone, and welcome to a new video. Today we are going to put object-oriented programming on the side, and we're going to talk about a concept. It's not really related to object-oriented programming, which is recursion. Recursion was one of those topics that you need to really have some sort of an imagination to be able to understand how does it work. Today I'm just going to start by showing you recursion is basically a method of solving problems. So far we learned how do we solve problems using iteration process, and I'm going to show some examples of those iteration processes that we talked about, and then I'm going to show you that same problem you can think about it recursively, and then you can solve them using recursion. Of course, you will notice sometimes recursion is a lot easier than iteration. Sometimes iteration is a lot easier than recursion. Either way, both of them will work. Um, Sometimes we go recursion because recursion is going to be more efficient, and sometimes we go iteration because iteration is going to be more efficient. So it depends on the situation that you have, but you need to know how do you solve both problems. Just to give you an idea about what recursion, if you look at those images here, you can see that I have an H in this graph here, and then if I can add more edges at the end of these ends of these edges, and if I add more edges, I can end up having something that will look like that. That's basically a recursion here. So of course, we need to understand what is recursion. We're going to define recursion, and we're going to talk about recursion, and we'll see how it does work. So before we do that, let's jump straight to Eclipse here, and let me show you an example here. What I'm trying to do here, I'm trying to find out what is the factorial of a number. And a factorial of a number is the number multiplied by itself minus 1, and then minus 2, and then minus 3, and then minus 4, until you get to 1. For example, if n equal 5, let's just put it there as a comment, if n equal 5, then factorial of n, which is 5, equal 5 multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. So that's basically what I'm trying to find out here. That's the method that we have here. So basically this is the method. I'm passing the value n, and then in the body of the method I declare the variable I call the fact. I assigned it to 1, and then here I have a while loop, or you can go with a for loop. This is the iteration process. This is how we think about problems most of the time. So I'm saying here, as long as n is greater than 1, I want you to multiply factorial by itself, Sorry, I want you to multiply factorial, which is 1 here, by n, and assign it to fact. This is, again, if you're not familiar with this, this is equivalent to fact equal fact multiplied by n. So I'm going to update the value of factorial by multiplying 1 by 5, and then I'm subtracting 1, 5, and 5, so I get 4, and then I go back 4 here. 4 is greater than 0, so it's going to be, after that, I'm going to go back to this this equation here, or this statement, so it's going to be factorial equal factorial multiplied by n, which basically means 5 from the previous operation multiplied by 4. And then after that, subtract 1 from the 4, it's going to be 3, and you go back here, then it's going to be the previous value, which is basically 20, multiplied by 3, and so on, until you get to the fact that n is going to actually equal 0. And when n equals 0, then this condition is going to be false. You leave, and you return fact. So this is, again, a very straightforward implementation of a method to find factorial of a number using iteration. Now, what is, or how do I solve this problem recursively? Before I do that, we need to understand what is a recursive and how does it work. In general, and this is just fact, when we have complicated problems, one of the methods that we can use to solve complicated problem is by reducing the size of the problem. So again, you have a problem, you can reduce the size of the problem, and when you reduce the size of the problem, the solution is going to get easier, and then you keep reducing the size of the problem, until you get to a size that you know how to solve it. And then after that, you go backward and try to solve the problem here. So you may ask, what does that mean? Let me just show you an example here. So we are talking about factorial of 5. Well, let's say this is basically how we write it. Now, factorial of 5, if you think about it, it's basically 5 multiplied by the factorial of 4. So as you can see here, I did have a problem, which is factorial of 5, which I didn't know how much is it, but somehow I was able to convert this problem into another form, which is basically 5 multiplied by factorial of 4. Now, I know what is 5, but again, I don't know what's factorial of 4. If you look at factorial of 4 and you compare it to factorial of 5, it's the same problem, but the size is smaller. Instead of 5, it's 4. So what I can do, I can leave it at this point, and I'm going to take factorial of 4 and think about this as a problem. Well, factorial of 4 by itself, if you think about it, it's 4 multiplied by factorial of 3. And here we go, I'm at the same position again. I know 4, but I don't know what is the factorial of 3. And again, I know what's factorial of 3, but I'm just imagine this is way more complicated than just factorial of 3. So what I'm going to do, I'm going to take factorial of 3, and I'm going to think about it recursively. This is basically what I'm saying here. It's basically 3 multiplied by factorial of 2. And then you take factorial of 2 equal 2 multiplied by factorial of 1. Now, this is very, very important when you get to this point. Now, I know factorial of... Now, let's try to think about what is factorial of 1. This is what we call the base case here. The base case basically means when you get to the end of it, and you know what is the solution of this here. At this point, I know factorial of 1 is basically and simply 1. So what I'm going to do, I'm going to take the results of this and replace it here. So I'm going to end up here, factorial of 2 equal 2 times 1, which is basically 2. And then I take the 2 results from here, and I replace it here. Remember, 2 is factorial of 2, so it's going to be 3 multiplied by 2. And this equals 6. So 6 is the factorial of 3. So you take the solution of this and you apply it here. So you get 4 multiplied by 6, which I think is 24. So you get 24 here. This solution here, you take it and you replace it. So it's going to be 5 multiplied by 24. And the final results of factorial of 5 is going to be 20. This is simply how do we think about factorial. So, about recursion, sorry. So the idea here of recursion is simply, could be described simply by having a big problem, and you break down this big problem into a solution that you have and a smaller version of the original problem. And then you take that smaller version and you apply the same concept, you divide it into another solution that you know and a more simpler version of the original problem, and you keep going in that way. This is very important here to understand that you must get to a base case. You cannot have recursion without getting to this base case because you're going to keep going, keep going, keep going. Now, a lot of people think about recursion as a dream inside a dream inside a dream inside a dream. At a certain point, you need to wake up. That's the base case. Now, another people think about recursion in a form of it's a picture inside a picture. And there will be a point where you're going to stop. And that's basically how we think about recursion. And so, any problem that we can solve using iteration process, by iteration process I'm talking about for loops, you can solve it recursively. But you have to understand that sometimes we go iteration, sometimes we go recursion. It depends on the problem itself. I'll show you some cases where recursion could be a good choice, and I'll show you some cases where recursion is not a good choice. But either way, you should know both of them. Let me tell you something. You will see a lot of recursion in the future in your life. So if you don't understand it, then you're going to have trouble. So you must understand what is recursion. Now I'm going to go back and show you how does it work inside the computer itself. But for now, we're just trying to have an idea about recursion. So what I'm going to do, I am going to create a new file here. And let's go back to Eclipse. So this is my factorial function that I just created using iteration process. And now I'm going to create another one. Let me just copy this. Of course, I'm going to get an error because they're identical. So I'm going to put an R here just to make it different. And I am going to take all this away. So we need to figure out how do we solve this problem recursively. Well, let's start with a base case. Usually, let me just put it this way. I'm going to update whatever I'm going to type here. I am going to say return n multiplied by factorial of n minus 1. Now, this is me creating a recursive case, but without having the base case. Now, before we do this, I want you to think of something that's a little bit different. You see here, this is factorial r. And what is this? Factorial r. So technically, let's just define recursion technically. Technically, recursion is having a function where you call it inside the body of it. Well, that's basically what makes it a little bit complicated. But here it is. I have a function called factorial r, and inside factorial r, I'm calling it itself. And look at this. I'm having n, as it is, multiplied by calling the same function, only this time I'm subtracting 1 from n. Now, here, obviously, I didn't take the base case under consideration. So here's what I'm going to do. I'm going to come here at the top. I'm going to say if n double equal 1, return 1, because we know that the factorial of n, if 1 is 1, else return this. And that's it. Now you may think, how is that going to solve the problem? How is that going to work? Well, before we do that, here I call the function factorial the tradition one with the iteration, and it gives me the result of 120. Let's close that, and now I'm going to just put R here just to show you I'm going to get the same results. And here we go. Now you may ask the question, how exactly this is going to work? Well, I'm going to show you how does it work and how the computer handle a situation like this. And let's go back here. What I'm going to do to simplify my work, I'm just going to copy this part. And let's go back here. Where is it? Let's add a text. Oh, okay, that's acceptable. We'll just move it here. And now let's go back and click here, go up. Okay. Now, what I want you to pay attention here, let's just take n as an example here. When n equals 5, we go and check the first case, which is n equals 1, which is not true, so it's going to go to the else, and this is what's going to happen. The compiler will just going to notice that, well, I have a return statement, and this return statement I have, let's say, 5. Oh, I hate this. One sec. Let me fix this. I have 5 multiplied by the factorial of 4. F is for factorial. Now the compiler will say, I have no idea what is the value of factorial of 4. So what's going to happen? The operating system is going to reserve a space inside the memory. It's going to call the stack. And in this stack here at the bottom, you're going to store 5 times factorial of 4. And then after that, the compiler will just put this on hold because, again, for me to be able to return the factorial of 5, I need to know what is the factorial of 4. And since I'm calling factorial of 4 at this point here, so I'm going to wait until I get the results. So back, you're going to move from this point back here with the value of 4. Now again, 4 doesn't equal 1, so you're going to skip that first statement, then you're going to go to the next statement, which is return 4 multiplied by factorial of 3. The compiler will find himself facing the same problem. So what's going to happen, the compiler will go to the stack again, reserve a space at the top of the previous space, and it's going to store 4 times factorial of 3. I'm trying to improve my skills in drawing, but it's not working. And after that, the compiler will go back and call the function, but this time 3 is going to be passed. Now, again, 3 doesn't equal 1, so it's going to get to the point, well, oh, I have the same problem here. 3 times factorial of 2. Go to the stack of memory, reserve and use space, store 3 times fact of 2. Same thing was going to go back here. You're going to call the function. You're going to pass 2 this time. And then you're going to end up having 2 times factorial of 1. Reserve and use space. Store 2 times factorial of 1. Sorry. And then after that, you're going to pass 1 back to the function at the top. And then you're going to have oh, look at this, it's 1. So this condition now is going to be true. So it's going to return 1. Now, that return 1 that we got from this statement here is going to replace factorial 1 here. So as a result, now I know what is the factorial of 2, which is basically 2. You take the result 2 here and you replace it with the factorial of 2 that you see here, and you get the results of 6. You take the 6 here and you replace it with the factorial of 3 that you have here. So you get 6 multiplied by 4, which is 24. You take the result of 24 and you replace it with the factorial of 4, so you get the results of 120, and then the compiler will return 120 back when you call it. I know it's a messy, but this is basically how it works. So as you can see here, this is how factorial works. You may think about this, well, why don't we just use iteration? Well, here's the thing. This is a case where I believe iteration should be a lot easier. Why would it be a good choice to go with iteration here? Because the stack here, the stack that you see here, this mess, let me just highlight it, this mess here, this takes a space inside the memory. So when you think about it efficient-wise, iteration could be the better solution in this case. But sometimes that's not the case. There's a lot of problems where if you think about it, if you want to write an iteration process for it, you'll end up having a really, really complicated low code. But with recursion, you can replace those hundreds of lines of code with 2 or 3. So it's going to be more efficient to go recursively. So this here is just to show you an example of how recursion works, and we're going to see a lot more examples in a sec. So as you can see here, this is the factorial using recursion, and this is the factorial using iteration. What we should notice here, and as I said before, if I want to define recursion technically, it's basically a function that keep calling itself. That's basically how we call it recursion. But every time you call the function, the size of the data need to be reduced. This time it's reduced by 1, sometimes it's reduced by half. So the size needs to be updated to be lower. So because when you reduce the size of the problem, the solution will be easier. Also, you always have to think about having a base case. So before you do anything, what is my base case? You have to think about that as well. And that's basically what recursion is, and this is just an example to show you how recursion works. Now we do have more examples. Let me see some of them here. We got computer factorial. There's some animation here. This is just what I did in a sec, the stack, and how the solutions will go back. Oh, Fibonacci number. Okay. Now, Fibonacci number, or series, it's something, I don't know if you know what it is, but the idea is very simple, and I'm just going to show you that. Here it is. We start, well, some references like to start from 1, 1. They don't start with 0. Let's just put it that way. I'm going to go with whatever the book is asking me to do here. So we got 0, we got 1, we got 1, we got 2, we got 3, we got 5, we got 8. You may ask, where are these numbers are coming from? Well, basically, you do have the first two numbers, which is 0 and 1. And then the third number is the summation of the previous two numbers. So 0 plus 1 will give me 1. Now, when you want to find out what is this number, it's 1 plus 1. So you get 2. And then if you want to know what is the number that you had here, this one here, let's imagine we don't know what, you don't see it's 3. It's 1 plus 2. You get 3. Then 2 plus 3, you get 5. And 3 plus 5, you get 8. 5 plus 8, you get 13, and so on. It sounds good. It sounds easy. The question is, what is this series of numbers? Well, they believe this series of numbers has something to do with how the universe is designed. Because they said if you take, at a certain point, not at the beginning, the number and you divide it by the number next to it, you'll get the same value. I tried it. Yeah, it is correct. I don't know, remember the value, but if you divide this by this and then you divide this by this, you will get not exactly the same, but something very, very similar. And and I'm pretty sure there's a lot of graphs that you saw somewhere. Let me just show you some images. Here it is. This is the Fibonacci number. This is how it looks like. They did a lot of studies and they found waves, for example. They took Fibonacci numbers here. There are some examples in real life how Fibonacci numbers is formed. The universe is Fibonacci number series. The ratio between your body parts, the nose and the eyes distances, and the legs and your arms and all these kind of details, if you divide them, you'll get the same Fibonacci numbers. Again, we don't have to worry about that for now. Let's just get back to Fibonacci number and how do we solve that Fibonacci number. Now, your job basically is, if I give you a location or a position of a number, for example, here this is 21, so 0, I don't know if they come from 0, 1, but let's just go ahead. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I tell you what is the Fibonacci number at location 9, so this is it. This is 21. So your job is basically to calculate and tell me what is that value. Now we're going to solve this problem using recursion, and we're going to solve it using iteration. And you'll see that recursion is a little bit easier, to be honest. Okay, so let's go back and try to solve this problem here in this area. So I'm going to go ahead and do public static. It should return an integer, of course. So Fibonacci numbers, and I'm going to put I here for iteration, and you're going to pass the position that you're looking for, and I'm just going to call it n again. And I need to do the same thing here. Let me copy this and go down here, and this time we're going to put R here for recursion, our recursion version. Okay, so let's start with this one. I need to have two numbers. The first one I'm going to call it first. I'm going to set it to 0. And then I will have a second, and I'll set that to 0 as well. Oh, sorry, 1, not 0. And this is what I'm going to do. I'm going to say for And let's see here, what do I do in this area here? I need to have the Fibonacci, so integer Fibo. I'll set that to 0. And here in this area, I'm going to put the for loop in a sec, or I'm going to maybe change it to while. But I'm going to say Fibo equal first plus second. Now after that, this is what I just told you. Now we need to update first and second. So what was second is going to be first. So first is going to be updated to be second, and second will be updated to be Fibo for the next iteration. So let me just put it this way here. If my, let's say I have first number equal 1, and let's just put a comma here. So the first equal 1, second equal 2, then Fibo is going to equal 3. Right after that, I need to update. This is just to show you an example. First is going to equal second, so first is going to equal 2 at this moment, and then second is going to equal 3. So when you go to the next iteration, Fibo is going to equal first plus second, which is basically going to give you a 5. So this is basically what's going on here in this area. Of course, I have to return Fibo. Okay, so we need to have a for loop here. What I'm going to do, I'm going to go with a while loop. And I'll say as long as n is greater or equal 0. Okay, and here I need to subtract n by 1. Now this part I'm not 100% sure if it's going to work or not. Let's just go back to the slide that we have here. So let's say 0, sorry, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to pass 9 to n, and I'm supposed to get 21. So let's call that function here. I'm going to say return 0 here so that I get rid of this error. Fibonacci, let's call this function. And let's go here, system dot out dot print line. Now let's just pass, we said 9. And let's see, hopefully we will get the 21 that we were talking about. Oh, where is it? Oh, well, let's go back. I got 89. And I think I know what it is. Is that the second? No, it's here actually. Oh. So we do have a problem here. Let's just go back and fix this part. So as long as n is equal or greater than 1. I'm going to fix that as long as it's equal or greater than 1 instead of 0. Yes, exactly. I just forgot about something. See? It's still showing me the value after that. This is exactly why I thought we should not have the 0 here. Okay. Oh, my bad. The reason why we already have 2 values here. Yep, I just forgot. Since I just have 2 values here, I don't need to include them in the calculation. Yes. And here we go. That was my mistake, and I'm sorry for that. So because I'm using first and second, so I already have the first 2 values, I don't need to include them in the calculation. Okay, so here we go. This is the iteration process. Now, how do I solve this problem? Recursion process. Well, the idea here, I will just do it so you'll see what I'm going to talk about. I'm going to come here and say return Fibonacci R. Now, any Fibonacci number, let's go back to this part. So, for example, Fibonacci of 20, well, did I delete 21 here? Yep, here it is. The Fibonacci of 21, what is that? It's basically, the Fibonacci at position 9. It's basically the Fibonacci value at position 8 plus the Fibonacci of position 7. So if you think about 9 as n, this is going to be n minus 2, and this is going to be n minus 1. And that's basically what I'm going to do. This is how simple it is. N minus 2 plus, I'm just going to copy this, Control C, and I'll put it n minus 1. Of course, now what I'm doing here will lead to a lot of problems. It has a lot of issues. This method. There's another method that, but I'm just trying to explain the idea here. So this is basically what it is. Again, I need to have the base case here, and the base case here is going to be if, and I want you to pay attention to this, n is less than 2 or less than 3. So if it's 1 or it's 2, let's see here, is it 1 or 2? Well, let's just try that and I'll see. Return 1. Else, return this number. So basically, if n is 1 or 2, return 1. And if you return 0, it's not going to affect anything. So yeah, this should be okay. Otherwise, what's going on? So basically, when you get to this, when you pass n could be a value between 1 and 2, and if it's 1 and 2, it's going to return 1. And if it's 3, that's not going to be the case. You're going to get here, and you're going to call this function and this function. And again, you're going to have 2 stacks for each one of them. A stack for this one and a stack for this one. And then for this stack here, you're going to keep going, and you're going to have another stack. So the idea here, if you want to imagine it, this is where it gets a little bit complicated. I don't want to draw it because it's going to be, like as I said, a little bit complicated, but I'm just going to give you an idea so you'll understand how does it work. So the first time you're going to have the factorial called, you will have 2 stacks. One will be here and one will be here. And this one here at the bottom will be the one when you call the function for n minus 2. And this is going to be when you call the function for n minus 1. So you're going to put one of them on the side, and you're going to go to the second one. And now we get to the second one again. Remember, you're going to call the factorial again 2 times. So you will have, at this point, 2 stacks, one here and one here. And then after that, you get to one of those, and this one will go and create 2 stacks, one here and one here. Let's imagine I got to the base case here. And when you get to the base case here, you got the result that's going to be passed here, and then you get the base case for the second one, you're going to pass it here, you get the solution for both of them, and you pass it here, and then you get this solution and you push it back here after you find the solution for that one. This is basically how the recursion will work in this case. The reason why this method is not the best way, because at a certain point you'll find yourself doing some calculations here and you will find them repeated here. So there's another solution for that, but I'm just not going to get into it. That's not the whole point of this class. So let's go back here and try to give this a try. I'm going to come here and replace this with an R, and I'm supposed to get 21. Let's see if that's the case. Oops, again, it's 34. So what am I missing here? It's this part here. As long as n is greater or equal 3. And there's a reason for that, and I'm going to show, no. And now it's working. The reason why I had to put it equal 3, because let's go back here. I know the solution for those 3. and I said return 1 if it's any of those, 1 or 2 or 3. That's the base case. And that's basically how the problem is solved for the factorial. Now, as you can see here, I do have two solutions, well, two examples, factorial and Fibonacci. Let's see if we have another example here. This is just a talk about recursive, think recursively, recursive helper function. Well, let me just, since I am here at the recursive function, I want to show you this. Sometimes when we think recursively, we need to have a specific case. Let me just take this one as example. I'm trying to check if a word could be read left to right or right to left will give you the same results, and I'm going to try to do this using recursion. So what I'm doing here in this example, I'm checking if the length of the string equal 1. For if I give you a word that has one character, well, yes, it's true. If you read left to right, right to left, it's going to be the same. Now, if that's not the case, what do we do? Well, here's what we do. We check the first character, and we check the last character. You see what I'm doing here? I'm checking the first character and the last character. And if they're not the same, well, obviously, that's not the case. You cannot read it from left to right or right to left. So return false. Now, what if both cases are not true? This is what I'm doing. I'm calling the function again, but what I'm doing here, I'm chopping the string. As you can see here, I'm using a substring from 1, so I'm leaving the character with 0, and the string of length -1, so I'm leaving the last character. And that's basically how it works. So basically what I'm doing here, I'm checking at the beginning if I have one character. If that's the case, return true. If that's not the case, check the last and the first character. If they're not the same, then return false and we're done. If that's not the case, chop the string. So what I'm doing here, well, if this is not true, what does that mean? It basically means it is. The first and the last character are the same. And then I go and move toward the center of that word. And I keep going, keep going, keep going, keep going. And as I'm going in that direction, that basically means I'm finding the first and the last character are exactly the same until I get to the end. Just let me show you an example for this here. Control N. Let's take this is a company in Kansas City. They do carpet cleaning. They call it Zero Res. As you can see here, this is, you can read it backward, forward, this is exactly the same. So what I'm doing here, I'm checking if I have one character. That's not the case, obviously. And then I'm checking the first character and the last character. Obviously, they're the same, so I'm not going to return false. And then I'm going to call the function, but this time I'm going to just pass this one here. And then I'm going to compare the I with the I. Oh, they're the same. So I'm going to pass this function. Then I'm going to compare this with this, and it's going to work. And then after that, I end up with one character, and that's basically how it works. Okay, so you see, this is how basically it works. Okay, so this is how recursive works when you try to figure out if a word can be read left to right, right to left. Now, the problem with this technique is every time you call the function here at the bottom, you're going to create a new string, which basically means that string, for example, if you start with one string, you may end up having 10 or 20, depending on the size of the string and how many characters there are. There's a fix for this solution. It's called the recursion helper function. And then, in this works, basically what we did, we updated the function a little bit. We started by creating a new function with the same name, and we're passing the string, and then we're going to call the function again, but this time we're not passing a string like we did previously. You see here, you call this function, you're passing a string. Instead of passing a string, where is it? I'm passing the string again without cutting it, so that's not going to generate a new string. It's the same one, and I'm passing the first index, the first character, and the index of the last character. And in this area, instead of calling the function again, passing a new string, I'm using the same string, but I'm just having new indicators for the characters. This is going to be move one step to the left, to the right, and then the high -1 move one step to the left. And that's basically how the string moving, the character scanning moves in opposite directions. Another example is what we call a binary search. Now, a binary search, this is a perfect example where using recursion, it's a lot more efficient. Let me see if I do have time or not. Well, the code is here, so I'll just leave it at that point. But let me just explain how does it work. Let's just go ahead and Control N. Well, first thing you need to know about recursion is recursion only works in sorted data. So if I have, let's say, 5, 7, 8, 10, 12, 15, 20, 22, 51. Yep, let's just go with that. Now, if I do have, for example, let's say 6 here, I cannot apply binary search anymore. Binary search, the data that you have basically should be sorted. And the idea here is to search for an element. I'm looking for an element here. I want to know if that element does exist in my set or not. So how does it work? Well, basically this is what we do. Let's see, how many elements do I have here? Got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that makes sense. And what I do, I jump into the middle, which basically, let's imagine I'm looking for the value 7. So you jump into the middle here, and you compare the value that you have in the middle with the 7 that I'm looking for. Now, if you find a match, lucky you, your problem is done. But if you don't find a match, you compare 7 that you're looking for with the value in the middle. If you found out that the value you're looking for is less than the value in the middle, that basically means the value that you're looking for will exist in this area. And if the value that you're looking for was greater, then that basically means it does exist in this area. Well, in this case, basically, the value I'm looking for is less than 12, which is 7. So it does exist in this area. Oh, it may not exist in this area. So what is that telling me? That's telling me that there is no reason for me to check on those. So that would be the first test to do. Now, as you can see here, by the first check, I eliminated half of my size of the data. Then after that, what do? We take the 7 and we take this part of the data. And you go and jump into the middle. Now, in this case, there is no middle value because I got 4 elements. So you got this one or this one. You feel free. You can go and use this one or you can go use this one. It's up to you. I'm going to just, for the sake of complexity, I'm going to choose 8. So I'm going to compare 7 with 8. And again, I don't find a match. And because I don't find a match, that basically means the value I'm looking for could be to the right of 8 or could be to the left of 8. Since 7 is less than 8, then that basically means it should be in this area. And since I have 2 values now, it's very easy. It's this one or this one, and you find the solution. And that's how binary search works. As you can see here, as we move on from one check to the other, the size of the data will basically reduce. Let me show you something really quick so you'll understand what I'm saying here. What I'm going to do, I'm going to put a value here, an extra value here. Let's put 2, for example. I'm going to put a value at the end of this. We'll say 61. And I'm still looking for 7. So what I'm going to do here, as I said before, since 7 is less, so it's going to be in this area. And then you jump into 7 and you find it. Now what I want to do, let's replace the 7 here with 5. So since 5 is less than 12, that basically means you go and compare it here. So at the beginning, I eliminate this. And then after that, I compare the 5 with the 7, and then I eliminated this. And then after that, I ended up in this area. So the binary search basically will help you eliminating the size of the data you're searching for by half every time you check for something. Now, This is how we think about it recursively, of course. Now the question is, what if I don't want to do it recursively? I will just take this away. Let's go back here and put the 2 here and put the 61 here. Oh, no, 6. Okay. 61. Well, if I want to search for the value, let's say 61 in this case, I basically need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 checks until I found the value I'm looking for. But if I want to do that recursively, check one time, eliminate those, check second time, eliminate those, and check third time. So 3 checks and I found the results. You see how efficient this compared to going through all the data? That's basically how we solve the problem recursively. Now I'm just going to jump into the PowerPoint to show you the code, and let's see, this is recursive implementation. Okay, so I do have a binary search here. I'm passing the array, I'm passing the key that I'm looking for. I have new variables. I'm going to call the first one low, which is basically the first character, and I'm calling the second one high, which is basically the last character. Those are indexes. And then I'm going to use a helper function. This time I'm passing the list again. I'm passing the key that I'm looking for, and I'm passing low and high. This is the function here, where after I'm passing, and here's what I do. First of all, I'm checking if low is greater than high. Low is greater than high, which basically that should be the case. Return, let's see here, this has to be without a match. So this is a case. I'm not pretty sure what is he doing here. Let me just have a look here. I think there's something typo here something. Let's just forget this part now. Let's just jump here into this part, and then I'll figure out what is the reason for this. I'm just going to calculate the position of the index in the middle, and then after that, I'm going to check and see if the key actually does exist in the middle. If first of all, I'm going to check if it was list. If it was list, look what I'm going to do. I'm going to call the low, and the high in this time is going to be the middle minus 1. So that's how I eliminate it. Now, if I find a match, return that variable we found it. Else, this is what I'm going to mid plus 1 to the high. So this is basically how it works. I am not pretty sure what is. Oh, this is okay. I see what's going on here. This is the case. If I keep going in this area, and I didn't find a match, this is basically where the low is going to be greater than the high, because as you can see, the low is going to be moved, and the high. That's my son playing video games. Low is moving to the high, and the high is moving toward to low. And at a certain point, the high is going to be greater than the low. I need to stop this and come back. Okay, I'm back. So here we go. This is basically the search process. This is the base case. What if I got to a point where the low is going to be greater than the high? Remember, the low represents the character to the left, and high represents the character index to the right. And that high should be greater than the low. But again, with the process, we're basically moving toward each other. And then as we move toward each other, we're going to get to a point where if I didn't find the value I'm looking for, the value of the low is going to be greater than the high, and this is basically where you have to stop. I'm going to stop with those examples here, and there's another example using trying to calculate the GCD, greatest common divider. This could be done recursive, this could be done using iteration. Let me just show you. Let me just show you how it works here. First of all, you have two numbers. You're trying to find what is the greatest common divisor. This is a non-recursive recursion technique. So what I'm doing here, basically, I divide or module T1 by T2. And remember here, both of them need to be positive values, so that's why I'm doing the ABS here at the top. So if T1 is divisible by T1. I'm going to get an R here. And if R doesn't equal 0, well, if it equals 0, that basically means T2 is the greatest common divisor. If that's not the case, I need to update those two values. And you can see here T1 is going to equal T2, T2 is going to equal R, and then R is going to equal T1 modulo T2. And then I'm going to go back and check and see if it equals 0 or no. Keep going that way. Recursive, basically, this is how it works. What I'm going to do, basically, return n if the modulo operation between them equals 0. Otherwise, you call the function again, but this time the first element is going to be n, and the second element is going to be m modulo 2. Otherwise, there is no greatest common divisor. Well, basically, greatest common divisor is going to be 1 anyway, if you didn't find any other values. So this will be the end of this video. The idea of recursion is not that complicated and it's not that easy. You just need to have a good imagination to be able to understand it. Of course, there's a lot of algorithms are used to solve this problem in real life. So this will be the end of this video. Thank you for watching. See you guys later.